Okay, it seems that we are on. So, yep, the webinar is about to start. So, as usual, let's give it last couple of seconds and then the webinar will start. Okay. So, Radek, can you see my screen?
Yes. I can see the presentation, the first slide, I guess.
Yes, I think
now
so.
Now going to full screen. Yeah, and now it's in full screen mode.
That's great. That's great. So I'll keep it.
Yeah, something is happening.
As
yeah.
it is. Well,
there's a video right in the first slide. Very famous one.
Yes. Yes, it is indeed. Yeah. So I think we can start. So I think we will.
Let's go for it.
We'll go for it. Yes. Okay. Hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we would like to show you and share with you a couple of tricks and tips how to perform external aerodynamics simulations. So I hope that all the information will be useful for you and will help you in your future projects. So let's get into it. Typical organizational information in the beginning. So the webinar is being recorded and the recording will be later made publicly available on our YouTube channel. So feel free to take a look, and I think we will send to everyone, to all participants and the registrants, we will send the link. So there will be a recording, so you do not need to make the notes. Just make yourself comfortable, sit, make a coffee, and watch and think what it is, what you need in your projects, what's helpful and what's good enough for you, because as you know, we are engineers and any problem can be as complex as hell. So think about it, what's good enough for you, and feel free to go for it. Yeah, so there will be 3 parts in the webinar. In the first part, there will be a general introduction. I promise I will be as quick as possible. I'll make it very promptly. Then there will be a more technical part where my colleague Radek will show how to set up things, particularly in our software in TCAE, which is based on OpenFOAM. And in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions. Use the time to the fullest. So ask your questions. We are here for you and we'll be happy to answer all the questions. The most representative questions will be answered right away here in the webinar. And those questions that are too specific or off topic or something, we will answer them later via email, but you can be sure that all the answers will be, all the questions will be answered, and that's, I guess that counts. Okay, let's make the last check. My colleague Radek Máca is hopefully here with us. So Radek, can you hear us? Can you see us?
Yes, I'm here. I hope you can see me and also hear me. So it seems yes.
Absolutely, we can hear you, we can see you, Radek. A pleasure to have you, because obviously Radek is the real expert here. So thank you, and I think we can start. So I promise I'll be very quick. No big too much details, but still I have to say a couple of things. So let's go. So yeah, still before the end of the year, there will be the last webinar, which will be dedicated to the Kaplan turbine, CFD, FEA, FSI, and optimization. So the last webinar of this year will be on December 19 on Kaplan turbines. So hopefully we will meet you there. And that's a little invitation for the last webinar. And yeah, so CFD Support is the name of the company. It's located in Prague, Czech Republic, 14 years old. And we deal with simulations, especially with CFD simulations. Later we have extended to FEA and FSI, and optimization and acoustics. So that's our main. Those are our main topics. We deal with these simulations. I would say that we have a product. The main product, the flagship product, is called TCAE, which is open source based complex product for simulations. It consists of software modules. There are a couple of modules. Anyone can play with them. Anyone can set up his or her own workflow, which fits their purposes, skills, experience, or resources. So it's really flexible. It's definitely extremely flexible. TCAE is developed in a way to be easily combined and scripted with other software pieces like other commercial codes, in-houses, or open sources. So it's extremely flexible, and it definitely helps the engineers to fit their purpose and their goals. Yeah, we have great, really great and efficient and specifically cost efficient licensing policy. Software is focused specifically on turbo machinery applications and on external aerodynamics. And in today's webinar, we would definitely like to talk about the external aerodynamics. So today it's so much more about the external aerodynamics. Otherwise, we have mainly for historical reasons, we have most of our users and our clients and collaborators are coming from the rotating machinery and turbo machinery industry, but today's webinar is about external aerodynamics, which means that typically an object is exposed to the flow and the flow is flowing around it, and the borders are relatively far away from it. So it's not the internal flows. That's the external flows. We call them external flows. Okay, TCAE, I'm coming back to the product, is focused, it's accurate, it's automated, it's well tested, it's benchmarked. A lot of information is available. So feel free to ask about the details. It's definitely easy to use. You can use it on laptop, PC, desktop, cluster, cloud, from home, from the office, of course, on Linux, on Windows, the same workflow everywhere. TCAE is based on open source. That's the best, I guess, the best part of it. We are a relatively small company, but we definitely mastered the ability of acquiring the open sources and turn them to be usable for the industry and to be really practically usable and connected well together to deliver the results, because we are engineers and we are here to produce the results, not to deal with the codes and scripting and etc. So this is the very large contribution we did. We've spent more than many years of the development in a team dedicated to turn open sources to be usable in the industry. So it's really big thing, and it's a lot of, I would say, added value added on top of open sources. You can imagine how much work has been spent on open sources themselves by their original authors, and on top of that, we've spent a huge amount of time dedicated development in a team. So really, it's really a lot of work has been done, and it can be seen in TCAE. We have recently released the new version of TCAE. It's called 23.10. There are a bunch of new stuff. I believe it's very useful for the future. We are focusing specifically on, I would say, three things. The first thing is optimization. big topic, paradigm shift. We believe that's a really big thing, and that's one of pillars of our focus. Then on acoustics is really specific, high-end, big added value thing. So TCAE definitely is being developed further. And the third thing, and perhaps the biggest thing, is called T-Base, the new module where we will allow the users to store all the simulation results in large databases, to allow them to mine the data, to use machine learning, artificial intelligence, and to create their own surrogate models to get the results of the simulation quality in seconds instead of hours or days. So it's really a really big thing. We believe it's a big thing for the future, and it will very likely disrupt the simulation market, and we are bringing it hopefully early next year. Okay, that's from me, and I would ask now Radek. I can still see myself, so I will switch the camera off, right? which I wanted to do. Okay, let's switch the cameras off, which I forgot in the beginning.
I didn't want you to interrupt,
Okay.
so it was fine
Sorry.
to see you live.
Right.
So.
Right. Thank you, Radek. So you yeah, okay. You saw me all the time. Okay.
Yeah. It was
okay.
very professional, so
Oh, thank you. Okay. Yeah, and anyway, so I'm switching the speaker. So I'm handing the presentation over to Radek.
Okay, so just let me know.
Yes.
You can see my screen perfect. All right, so today we will deal with the external aerodynamic cases. And first to mention is that a lot of case studies are available on our web pages, and many of them are specialized for the external aerodynamics, like this DJI propeller, for example. We have additional one, this Drifter car model, which is focused on the real car model modeling and revealing the drag coefficients and aerodynamical coefficients of this for this shape. Additionally, we have the Spitfire aircraft modeling, the same, for example, for wind turbines. So we can combine this external aerodynamic with rotating machines, and of course, this building flow around the building example. We have this airflow NACA examples, which can be also put into the optimization loop, like for studying different angle of attacks or even the parameters itself, the shape itself. And we have this Ahmed body, which I will use today, just start from the scratch and show you how simple is the workflow to set up the case. I'm not speaking about how simple it is to get accurate results, right, for very fine meshing and so, but I would like to show you the main principle of setting up a case from scratch to get the CFD results. So I will be using this Ahmed body, and maybe then we will mention additional examples with external aero parts and geometries, like for example propeller DJI, which can be connected to acoustic module, and you can also get both CFD results and acoustic parameters. So let's go for it. So I will open the TCAE, the new version 23.10. So I will open the GUI. The GUI looks very the same like the previous version, and let's start. So first of all, I will make it full screen, and I will create new project. And first what I will do is that I will save project to my disk. So my working folder for today is TCAE webinar, and let's say I will call it the Ahmed body, snappy, and webinar, for example. So this is the brand new project. And first, what we need to do is to create the computational mesh. So for this purpose, I can enable the tmesh module, which is used for generating or importing mesh. And let's go for the setup. So here we have the first menu, general, in which we can set the purpose of the meshing. So because we will do just for the CFD simulation, so we will leave this CFD mesh, which is set as default. And now you have options if you would like to import the geometry into the project, or you can keep the geometry as external. It means the project will access the geometry from some external directory for all the time. So if you move the project, you lost the connection with the original geometry. So if you work with some kind of one scenario geometry that you will import the geometry and then use it forever, then we always suggest to go with this implicit option, so to import the geometry. Or if you plan to apply some geometry optimization where you have some external tool which generates you new geometry variants by the external tool, then you should enable this external geometry, because from some kind of external directory, the geometries will be imported every optimization loop, and the external directory will be used as a place for generating new geometry variants. But in this case, we would like to import the geometry. So let's go for it. So I will import the geometry just to see it. So I go to the component menu, and here I will import new surface geometry, and here I put the STL of the Ahmed body. So whenever I import it, it will appear in our GUI, and we can see the shape of the input geometry. What I skipped is this rotation reference frame, which is used mainly for the rotating machinery. So in this case, I'm not setting up any turbo machinery case, so I can leave it as it is. And now I would like to create the external aerodynamics. Typically for the internal aerodynamics, you need to prescribe all the wet surface which defines your internal shape of your machine, of your geometry. In this case, you have two options how to define the shape of the wind tunnel or of the exterior which you would like to use for definition of the computational domain. If you are okay with a simple box-shaped aerodynamic tunnel, we can say it, then you can enable this add bounding box for external flows. So without the need of importing additional STLs, this shape will define you the external parts of the computational domain. So you just set which direction of the flow you prefer to simulate. So here the plus X direction is our inflow direction into the tunnel, and now we need to set a proper dimension of the bounding box. So typically the bounding box should be made large enough, and larger is usually better to get rid of any boundary effects, to really simulate the external flow without any effects of the boundaries. Typically, if the boundaries are close enough, then it basically influences the flow itself, or it increases the pressure before your or above your object and can influence the overall aerodynamic coefficients. So let's say the rule of thumb, if you put it in every side 10 times of some reference direction of your objects, now it depends. Typically, it depends on some kind of cross-section area. So how your object influences the flow around. If it influences more, then you need to make this bounding box larger. If it's just a thin obstacle, then the bounding box can be smaller. So let's say I will set up to 5 meters, because the Ahmed body here is scaled to 1 meter. So I will put 5 meters in front of my object. I will I will set 10 meters behind my object, and because the width and height of the Ahmed body is some kind of less than half a meter, then I do the same but with half of size. So for example, I will put it 4 meters on each side, and let's give it, for example, 6 meter height. So I think this is far enough for the dimension of the bounding box. All right, now we can go for the definition of the cell size or for the mesh refinement. So first, a parameter to set, some kind of basic parameter, is the background mesh cell size, which is the largest cell in the domain. So I can use cube cells, so hexahedra of an equal size for each in each direction. So for example, I try to set it to 20 centimeters. Here you can enable visualizing the wireframe. So this is the, let's say, visualization of this cell size or mesh size compared with your object. So definitely apart, far from my object, I don't need to have very fine refinement, but what I will need is to refine the mesh around my object and mainly, and also refine the wake area behind my object. So let's start with this. Just to have the simulation quick, I will set it in very rough way. I will set some rough mesh parameter to properly describe the mesh or the object, but we can't expect very high accuracy of the results, because the accuracy depends on the mesh refinement, of course. But to save some time and to run it live, I will set it in some rough way, for example. So compared to the sizing of the Ahmed body shape, let's say we will set the minimum level of refinement to 3. So each cell will be split 3 times for the flat areas and for the curved areas, and for the stands, let's say I will try to set the level 5. And typically, to have some kind of refinement at the bottom side of my virtual tunnel, I for example set level 2 at the bottom of my virtual tunnel, just to have a nice refinement near my rigid wall. Now the type of the boundaries, so the default is wall. The inlet and outlets are set automatically based on the direction I have chosen here. And for example, the minimum Z minimum, which is the bottom wall, which will be simulated as a rigid wall. So I will keep it as a wall, and the other parts will be, for example, I can set the symmetry. Yes, just to mimic the symmetrical behavior of the flow, and I don't want to simulate these parts or these walls as a slip wall or no slip wall. Sorry. So I would like to simulate it as a symmetrical wall. Okay, then what I need to put is to define the internal point. So let's make it the visualization smaller. So this point for external aerodynamic, for external flows, I need to put somewhere out of my shape, and it must be placed into the virtual tunnel region. Yeah. For the internal flows, of course, we are putting this point into our object, into our turbo machinery design. Okay, so this is okay. And what we can also do, which is important for external aerodynamical simulations, is to apply some local refinement region, typically in the wake area. So we can define or enable some kind of default shapes. So for example, here I will use the box, and I would like to define some kind of refinement in the wake area behind our Ahmed body shape. So we can put it so it's symmetrical. So let's first set the y direction. So let's start from 0.3, let's say, up to minus 0.3. The top part, we can go up to 0.4 meters, let's say, and I think this will be enough. Maybe we can go a little bit into the shape. So let's go with 0.2, for example, and okay, as an example, we can set it this refinement box, and we can put, for example, level 2 also to refine the wake area up to the level 2, which means split all the cells inside this box, inside this region 2 times compared to the original cell size. Okay, then for example, for advanced simulation and to have very good accuracy, we should also apply the boundary layers, but I will, let's say, skip this point. You can enable simply by setting up that I would like to have 6 layers on my Ahmed body, and in this way you can enable it. If you go to the advanced meshing options in the layer mesh parameters, then you can set the particular layer parameters like the first layer or final layer thickness and so on, the expansion ratio. So I think it's pretty straightforward, but for now, let's say I will uncheck this adding layers just to speed up the process as an example. And the last parameter to mention is number of processors. So my computer has 10 processor, 10 physical cores, so I will set 10 cores for the simulation. And let's click run all just to check if my rough setup will simulate or will generate a mesh which can be used for the simulation. Typically, you need to check if all your object parts are meshed properly, and of course then if the refinement is enough to get the accurate results. And typically when we start a new project, we do some kind of rough mesh which nicely describes your object and for which the simulation runs well, and then we can go for the refinement and finer meshing setup, and basically we are comparing to the previous results to somehow see the convergence to the real physical, let's say, or measured values of your object. Okay, the mesh was done. It was pretty quick. You can see we have now 220,000 cells, and to visualize the mesh we can click here to show the mesh. So now we can see the mesh, and to see what is happening inside we can click here on the CFD mesh, apply the slice, and okay, I would like to have it, this slice I need to have the normal in Y direction, so let's adjust this. I can set surface with edges, and we can see that we have, let's say, a mesh which nicely describes the shape, or nicely it describes in our object. The mesh is pretty rough, but we don't see any holes, we don't see any bad shapes.
Radek, Radek, I have just one note, just a quick note. What we are seeing here, it's a plane, right, which cuts the mesh, but these are not exactly the cell shapes, right? Maybe you should check off the triangulate the slice, right? It helps a little bit. Yep, this gives
exactly.
I think better view. Thanks.
Yeah, and what I would like to check, for example, also if the stands are meshed properly, so we can see that we have nice meshing around the stands. And as Lubos mentioned, we can also enable this crinkle slice, which really visualize the full shape of the cells which are intersected by our slice. Yeah, so as you can see, we can see that all the cells which are intersected by the slice as a 3D objects, basically as a 3D cells. Yeah, so this is basically the real shape of the generated cells. Okay, so this is some kind of first checking of the meshing, and if we are satisfied, we can go for setting up the CFD simulation. So we can go for the CFD module. So let's go for it. So again, just to be sure, I will save my current setup and go for the TCFD module. So here we can go from the top to the bottom and preset every parameter which is available. So let's start with the simulation type. So here for the external aerodynamic simulation, we have this virtual tunnel type, and basically we will choose it and then go for the additional parameters. Here we can set a steady state or transient simulation. Let's go for the steady state. I don't want to go into much detail, so we will simulate 1 point, 1 condition. Let's start with a 500 iteration, which should be enough for this rough meshing. For the finer meshing, you typically need more iteration to set because this simulation needs more iteration to converge. The flow is more complex, more internal patterns and wake area occurs, and the solver needs more time to find a steady state solution basically. In the fluid properties, we will stick with the standard R with the default parameters of it. You can, of course, anytime change it. Rotating reference frame, there is nothing to rotate, so we can skip this point. In the multiphysics, we can play with some additional processing features, like we can play with the porosity zones, for example, to simulate some kind of heat exchangers or whatever. We can also adjust additional models like the passive scalars and etc. For the turbulence, when we are in the steady state mode, we can set our favorite turbulence model. So typically we use this K omega SST. In case you would like to go for the transient, you can play also with additional models like DES for the detached eddy simulation type, both for the Spalad Almaras or K omega SST, and basically you can also have the more complex solution for your problem. So let's stick with the steady state. In the simulation itself, here in the solver setup, again I will set 10 cores, 10 processor to be used. Numerical order, I will go straight ahead for the second one. So I'm confident with my setup, but typically again when I start with the very first setup, I usually start with the first, second order, and if everything works, then I can go for the second one. Here in the runtime evaluated quantities, I can choose what quantities I would like to evaluate, what will be the averaging window to really have a nice steady state solution, typically some kind of 20% of the maximum iteration set. For further post-processing, after the simulation is done, I can, for example, require some specific fields to post-process. So for example, I would like to see the wall shear stress. For some turbulence visualization, I would like to see the Q criterion. I would like to see, for example, also the vorticity, maybe turbulence intensity as well. And definitely, I would like to see also not only the instant results, but I would like to also see the averaged time average or iteration averaged solution. So I would like to see the average pressure, average velocity, and that's for example, I'm fine with that. Efficiency probes is typically connected to the turbomachinery designs. So here I can leave it as it is. But for example, I would like to have a specific information about the force coefficients and aerodynamic coefficients. So I can enable the forces here. Here I will set that I would like to evaluate it on the Ahmed body. I will set the lift, drag, and pitch direction, which is basically the default one. So X is the drag and Z is the lift, as we can see. And what I would like to see set here is the reference area to have the aerodynamic coefficient scaled with respect to the shape of the body. So here I think the cross-section area is 0.115 meters squared. Reference length is 1 meter, and the reference velocity will be 40 meters per second. 40 meters per second, yeah. So this is what will give me drag coefficient, lift coefficient, momentum coefficient, and other forces acting on the Ahmed body. Here in the convergent check, because if the simulation converges quicker than my maximum number of iterations set, so I would like to have the results earlier and not to simulate all the iterations. So I can go for example, okay, skip here. Yeah, I will add a new one. I will not go for the efficiency probe. I will go for the force probe, and I would like to see, for example, that the lift average quantity is okay. I think the target value is something like 0.3. So I would like to have have the tolerance as 0.01, and for example, the same I would like to have it for the drag coefficients. So sorry, the target value of drag coefficient is 0.3, something like. So I will put it here, and I'm not sure about the lift coefficient, so I will get rid of it. Yeah, so the drag coefficient, if the drag coefficient over the simulation will be less than 0.01, the differences over the averaging window, then the simulation will stop. Controls is connected to the numerical parameters, so we can keep it as it is into the default values. Only what I suggest to check is these minimum maximum pressure if it corresponds to conditions and the expected results everywhere. In the scripting, we can put some user specific Python scripting which some kind of modifies the workflow in a way the user wants. Sorry, in inlet boundary conditions. So I will be quick here. So we can set either velocity profile, but here we would like to simply set the fixed velocity. So 40 meters in x direction. Turbulent inlet, so we can set the particular values for the turbulence quantities, or you can set it via some combination of turbulence intensity and, for example, length scale. So we can set turbulence intensity 1%, or length scale to, I don't know, 0.3 meters. And the reference velocity is also 40 meters per second. Outlet we can keep as fixed pressure, and on the walls, yeah, standard no slip walls will be modeled with a standard wall function in this case. And in the initial conditions, so initial velocity will be the same as for the inlet. Pressure is set to 0, the reference pressure, and we can use the inlet turbulence values, which will be evaluated from the initial from the conditions and the inlet. And in the post-processing part, we can somehow play with the report. We can also add turbomachinery design, so turbomachinery specific evaluations or visualizations. So this is not applied here. We can have some specific sampling on the Ahmed body for further processing. So you will get the data files with all the values on the surface, and you can also write machine in different, or write the results in a different formats. Okay, so I think we set what we needed, and now I save my current setup and go for the simulation. So keep fingers crossed. Now we will see how the simulation runs. We can, for example, create several line charts to visualize, for example, the drag coefficient. So I can enable these quantities, go to the display, get rid of the default quantity which is visualized, and go for the drag coefficient. Now, for example, in the view, so I can focus when I click here. Now I can focus on the current data, and here I can, for example, adjust manually the y-axis to from 0 to 0.6, so 0.2, let's say, and now we can see the current drag coefficient for this very rough mesh is something around 0.43. If we go back to our web pages, to our Ahmed body example, you can find the report of this benchmark, and I think somewhere here, yeah, we can see the real values, which is 0.28 of a drag coefficient. And now, yeah, the simulation can converge pretty quickly. And just to see the results, okay, maybe we can wait for the final report, which show us that the drag coefficient equals to, where we find it, let's find the proper part, or maybe I missed. Okay, so let's go back to the TCAE, to the setup, to the report, and maybe I missed to check the most important part. Yeah, to enable these force coefficients. So I will get rid of other quantities. Okay, and I will keep just the force coefficients there, so I can click save again. And now I can regenerate the report, so full CFD report. And then we will be able to read the final value for the drag coefficient on this very rough mesh, which is, I can go here, forces, force coefficient, so drag is 0.43. So as we can see, we are far from the real value, but for the mesh which is extremely rough. So as an example, if I, for example, made some kind of little bit, I make the refinement a little bit more. So I refine the surface, and for example, what I can also do is to increase the cells between levels. So it's some kind of level of graduation from the courses level to the final level. But basically, there will be more levels, more cells refined according to each level. So I will adjust it and try to run it. So let's remember, okay, 0.44 was for this very rough mesh, which counts some kind of 220,000 cells. And now, just as an example, I just redefine two numbers. I can save it and run the whole workflow by one click and just wait for the results. And basically in this way, you can play with refinement and find the proper combination of accuracy and the number of cells or the refinement level for your mesh. Okay, so and when the simulation will be finished, so maybe meanwhile, I can show you an example for the TCAE propeller, just to see that the workflow is very similar, except that there is a rotating region. So let's go for the TCAE here in the tutorials, TCFD put TCAE, and I can open this project. Just a quick overview while our Ahmed body simulation is running. So in this case, we don't have this bounding box for the external domain simulation or definition. Here we have a simple sphere defined by two STLs. Yeah, so domain in we have here and domain out, and inside the domain, so if I display it with some opacity, we have some, so this is some kind of evaluation surface for the acoustics, but inside, I will get rid of it, but inside there is a rotating region with I will get rid of this selection. With the propeller itself, so we have two components here. First is the external one, and in the middle there is a rotating region component with the parts of the propellers, and all the other basically parts of the workflow is very the same. So at the inlet we have some specific boundary opening because the suction is done by the propeller, rotating propeller itself. And in these rotating reference frames, we have now set the rotating region for the propeller. And in case of for the acoustics, you just define the acoustic surface, which is defined here in the runtime evaluate quantities. You can define here, right, acoustic data. You defined how many data you would like to measure, at which surface you would like to measure the fluctuation of the pressure. And then in TCAE module, you just say for which data you would like to do the analysis. You define the observers, so points within the space where you would like to measure the sound, which is stored on your acoustic surface. And at the end, you will get a nice report about the acoustic data and frequency analysis. Okay, so very quick, but maybe my time is almost up. And back to the Ahmed body. I'm not sure if the simulation were performed. So let's see, running TCAE module. Recalculation done. Okay, I'm not sure if I clicked the proper. So let's check it. Maybe I need to rerun. No, sorry, this was not the one. We save it. Okay. So calculation is skipped. So I'm not sure if the simulation were running. Maybe I didn't. Maybe I just click the mesh generation. So let's check it again. Okay, so let's change the number of iteration here. And let me try to rerun the simulation. And maybe meanwhile, we can slowly go back to Lubos. And now the simulation is running. So probably I just hit the running mesh and not running the whole simulation. Oh, but let's go for the checking up the values.
Yes,
but
yeah. This is not that important. I think we've got it. Thank you very much for your part. It was very informative. Thank you very much. Yeah, and I'll slowly get back to the.
And just we can see now that really the drag coefficient is much lower, much closer to the.
Yeah, I'm sorry. I just stealed. Yeah, I just stealed the presentation back.
Okay, no problem.
so the audience, the audience can't see it. But anyway, we can get back to you if that's okay. I have a couple of notes here. So I would like to ask the audience to ask your questions. So please ask your questions. Ask about anything. We will sort it, and definitely will be happy to answer the representative and the relevant questions here. So feel free to ask your questions, and I will continue with a couple of notes I made here. So first of all, you have just seen a specific setup in TCAE, but you can be sure that the principles are valid for most of the finite volumes based codes. Globally. So these principles are valid pretty much everywhere. These as you noticed, there are a lot of details, right? So there are so many details. All the cases are extremely complex, and there are so many parameters everywhere. The fact is that not all the parameters are important. Not, of course, all of them are important, but not all of them are important in the same way, right? So there are extremely important parameters, and then there are just important parameters, right? So I know it's quite a mess, but setting up the simulation and get some results is relatively straightforward, and anyone can do it. Any engineer can, after 1 or 2 day training, can set up such simulation, as you have seen now, this Ahmed body, and get relatively good results or acceptable results, and it's relatively easy to make them better and better. But as you know, the devil is always hidden in the detail. Here is a simple plot where we have plotted our thoughts about the project accuracy, the CFD accuracy, versus effort that has to be spent to get the particular results. So, for example, if you had really great measurement of some let's say flow around the object, let's say the drag coefficient, like in this case of Ahmed body. So if you had such a really great measurement, you believe that's completely true, that would be I would call it would be this red line, right? That means that any simulation you do can get closer and closer to by a couple of percents, right? So this percentages means the difference from the what you think it's perfect, what you think is absolutely correct, which is almost never, but yeah, it's a thought experiment, right? We are thinking creatively how things could be. So the thing is that it's relatively easy to get 5% away from the benchmark, because you could, let's say, make, I would say, 15 issues, 15 specific decisions are to be resolved properly. So if you make 15 good choices, then you could be easily in 5% range from the perfect results. But you know what's perfect. But anyway, the thing is that the effort it grows exponentially when you are closing to the perfect results. So for example, if you want to be like 2% of the accuracy, 2% away from the benchmark or from what you believe is perfect, then you should make perhaps 30 decisions really great. And it closes, this is just a simple sketch. It doesn't mean any particular case, but I guess you get the point. If you want to get to 1% away from the results, you believe they are perfect, you have to make so many tens, perhaps hundreds of decisions correct, and that might be a problem. So the point of all this, the point of all this I'm talking here is, any CFD project is always a trade-off between the effort you spend on it, either spent on time or money or the taking the decisions and reading new things and trying here, trying there, and the accuracy what you achieve, right? So it's always a trade-off. And the question is, when you are fine, what's your level of accuracy you are fine with? That's all. That's the biggest question, and all of us have to frankly and honestly answer this question, because it's very critical. Okay, so that's point I wanted to make. By the way, we have written such an article which is called CFD Project Accuracy versus Effort, and it can be found on LinkedIn. So you can read more details about this this topic. What's extremely important in external aerodynamics is the size of the computational domain, right? The virtual tunnel. The practice show that the bigger is always better. So the bigger virtual tunnel, even it looks insane. Sometimes it's really huge. It's tens and sometimes hundreds times the size of the object. But yes, really to move the borders really away from the object helps, almost always. The second order for all possible quantities is also very helpful. In the external aerodynamics, it definitely helps. In the internal aerodynamics, it's not that simple. You can go easier, but in external aerodynamics, the order really matters, and also the effect of turbulence. Of the turbulent effects are critical. So the choice of turbulent model, we didn't talk about it much because yeah, it's a broad topic, but yeah, definitely turbulence model makes difference. And of course the mesh size changes everything all the time in CFD, in finite volume CFD, because it decides about the time of the simulation time, and simulation time is always the huge question for all simulation engineers. Okay, so the time is running very quickly, so let's get to the questions. Radek, can you see any questions? Any question you would like to answer? Radek, can you hear me? Maybe your microphone.
Okay, I'm back.
Yeah.
I'm back.
Yeah.
Yeah. Maybe I will pick one. Do you have any parameter control to obtain good results in the simulation? So basically in the report. So maybe if I can show you.
Yes,
or
I will share.
just
I will make you presenter, Radek. So now.
Okay, show my screen.
Yes, we can see your screen now.
Great. I will just get rid of this window and okay. And here in the final report, which is automatically generated, we have some kind of icons. So very quick check if the flow rate set fits at the inlet, at the outlet, if there is no bounding limits to the cell. So if there are some cell with an unexpected value, and if the residuals goes down and are below some standard levels, so then if you see all the icon in green, then there is high probability that your results are okay with respect to what you set as a meshing parameters, inlet values, and so on. Yeah, but it's always up to the engineer which controls the final simulation data if they are okay and so on. Yeah, so this is the, let's say, the first check to see if there is no any bug or any divergence and so on.
Okay. Yeah. We have another question from Tarakaram. He is asking in which industry CFD is most used. Yeah, CFD is computational fluid dynamics. That means that anywhere where the fluid flows and comes makes an effect on objects. So the usage of CFD is pretty wide, I would say. So it's definitely everywhere in the mechanical engineering, yeah, and also in the structural enginering and civil engineering, and it's pretty much it's in medicine. It's pretty much everywhere. Turbo machinery field is a relatively big field, and we are very active in the field of these turbomachinery. That means rotating machines like fans, compressors, turbines, etc. Yeah. So CFD is, yeah, I think you can Google this easily. So I'll skip this. Bistrik is asking, is there a tutorial case in your database of a free stream flow into an ambient environment, e.g. modeling of streams, temperature mixing? I don't know how exactly to answer this. Perhaps this should be a this is a candidate for an email discussion, because I'm not sure if I'm getting this well, and I could mislead you. So sorry. Let's come back to this via email. And yes. Can you? Yes. Nasir is asking, yeah, it's a question. I'm working on hydro turbine. I need to complete learning CFD on simulation of specific study of cavitation of Francis turbine. Okay, listen, we made a couple of webinars about Francis turbine, and in 2 weeks there will be a webinar on Kaplan turbines, which is, I believe, very similar in principle, extremely similar. It's basically the same, the details and etc. So let's get in touch there. Yes, we definitely support Kaplan and Francis and hydro turbines. So feel free to get in touch with us. Yes. Radek, can you see any questions you would like to answer?
Unfortunately not. So
are you aware of anything you would say?
Nothing comes to my mind. So maybe if you have any question for later, don't hesitate to contact us. And at this point, I'm fine.
Okay. So yeah, I think perhaps it's time to conclude. We're definitely open to answer all your questions. So feel free to ask about anything. We would definitely like to support you. We would like to help you with everything you want. It's our job, and we like it, and we are happy to help. So I guess this would be it for today.
Yeah, thank you for watching, and hopefully see you next time.
Absolutely. So thank you for coming, and bye-bye for now.
Bye-bye.